I hope you can hear me, everybody. It's a pleasure, particularly for me, to introduce Tim, who I've known for a very long time. He's now research professor at the Finnish Environment Institute. He wrote the IPCC technical guidelines, the first set of them on methods of climate impact and adaptation assessment, copies of which I was trying to find in the bookshelves behind me. I can't see myself on the screen, but I'm holding up the book version of that. The technical guidelines themselves that are still on the IPCC website and have been updated over the years provide a good introduction to how climate impact assessment is done by social scientists and physical and economic scientists, and how adaptation assessment is also. And that's important because in order to give an informed judgment, as it were, to the reader of impacts and adaptations that one reads about in the forthcoming chapters in this volume, indeed in any IPCC or other volume, it's important really to understand something about how their work proceeds, what precision surrounds their judgments, and what caveats the reader, as we heard in some of the Q&As, the reader should be familiar with. After that, Tim went to be a member of and later chair of the IPCC's task group on methods and analysis and data for IPCC assessments, the TGCIA, the task group on impact and climate and adaptation and assessment. So he's now reached some dizzying heights. And I'm always surprised that 40 years on, having been saddled with the ball and chain of being a research student under one Martin Parry at the University of Birmingham, England, not Alabama, he's broken through that particular glass ceiling to become research professor in one of the major environmental institutes in Europe. Well, that's what raw scientific talent can do. So, Tim, will you please speak to us about climate, let me get the title, Assessing Impacts and Adaptation. Tim Carter.
You see that?
Yes, thank you, Tim. Please go ahead.
So thanks a lot for the introduction, Martin. I'm Tim Carter from the Finnish Environment Institute, or SYKE, in Helsinki, Finland, and this is the first of 5 lectures in section 2 of the series that focus on methods and approaches. This one attempts to provide an overall introduction to the assessment of climate change impacts and adaptation. That's quite a formidable challenge, but I'll try to cover at least a core set of issues that my colleagues can offer much more insight into in the following lectures. As such, I'll also try to reference upcoming lectures at the appropriate points. So here's what I plan to cover. After introducing the topic that these lectures are built around, climate change impacts and adaptation, we can then explore how the topic is commonly framed for research and policy, what issues are typically studied, what methods and tools are used to do this, and how analysts specify uncertain future developments in order to inform strategic policy development. And finally, by way of conclusion, I'll summarize some of the more notable trends in the field and emerging areas of inquiry. So first things first, why do climate impacts matter? Well, we've just heard that they matter first because we know that the global climate has been changing rapidly during the past century. The figure here is from the special report on global warming of 1.5 degrees from the IPCC. And as we heard, observed global mean temperature for the decade 2011 to 2020 was about 1.1 degrees Celsius higher than the average over the pre-industrial period. So climate impacts matter second because the changes in climate shown on the left are causing impacts. And the figure on the right from the IPCC's 5th assessment shows that changes in climate over recent decades have caused impacts on physical, biological, and human and managed systems on all continents and across the oceans. The IPCC sixth assessment, just released, reports that human-induced climate change has caused widespread adverse impacts and related losses and damages to nature and people beyond natural climate variability. Climate impacts also matter because policymakers worldwide need to find responses to avert their potentially adverse effects. The impacts of human-induced climate change that have already been observed are projected to intensify, and some may become so adverse that they could threaten food production, economic development, and the ability of ecosystems to adapt. As shown here, these concerns about dangerous interference with the climate system led to the signing of the United Nations Framework Convention on Climate Change in Rio in 1992. Since 1992, in spite of international efforts to reduce greenhouse gas emissions, they've stubbornly continued to grow, and global temperature is rising in response. And in Paris in 2015, as is shown on the right, it was agreed that efforts should be strengthened to contain the global temperature rise to below 2 degrees Celsius above pre-industrial levels, and pursue efforts to limit this further to 1.5 degrees above pre-industrial levels in order to significantly reduce the risks and impacts of climate change. This should be achieved by increasing the ability to adapt to the adverse impacts of climate change and by fostering climate resilience and low greenhouse gas emissions development. So what do we mean by climate change impacts and adaptation? Note that the IPCC adds vulnerability alongside these terms in the reports of its working group 2. And climate change impacts, adaptation, and vulnerability are sometimes referred to as just CCIAV or IAV. And here are some IPCC definitions which have evolved somewhat over the years. Quickly go through these. Impacts are the effects on natural and human systems of extreme weather and climate events and of climate change. Adaptation in human systems, this is the process of adjustment to actual or expected climate and its effects in order to moderate harm or exploit beneficial opportunities. In natural systems, adaptation is the process of adjustment to actual climate and its effects, whilst human intervention may facilitate adjustment to expected climate and its effects. Adaptation plays a key role in reducing exposure and vulnerability to climate change, where vulnerability is the propensity or predisposition to be adversely affected. So now let's consider the different approaches used to investigate climate change impacts, adaptation, and vulnerability. The columns in the table shown here from the fourth assessment report of IPCC distinguish 4 general approaches, though others might use slightly different categories. The impact approach was dominant until the turn of the millennium and is still popular. This aims to evaluate the likely impacts of climate change under given scenarios of future climate and to assess the need for adaptation and/or mitigation to ameliorate these potential impacts. Vulnerability-based approaches concentrate on describing the propensity to be harmed and the actions needed to avoid or to reduce this. The adaptation approach focuses on identifying and appraising different options for building adaptive capacity and resilience to risks posed by climate change. And then integrated approaches include integrated assessment modeling and other procedures for investigating CCIAV across disciplines, sectors, and scales, and representing key interactions and feedbacks, including synergies and trade-offs with mitigation. The standard impact approach is often described as top-down because it combines scenarios downscaled from global climate models to the local scale with a sequence of analytical steps that begin with the climate system and move through biophysical impacts towards a socioeconomic assessment. And lectures 3 and 4 provide examples of this approach. Bottom-up approaches commence at the local scale by addressing locally relevant climate-related risks, which are commonly location-specific. Vulnerability approaches and adaptation approaches are usually categorized as bottom-up approaches. The approaches tend to be participatory, involving local stakeholders, typically relying on recent and present-day experience, and with a focus on supporting decision-making. And lectures 5 and 6 will offer some perspectives on these approaches. On the right are listed some recent trends in CCIAV research that I've identified. These and other trends are taken up in subsequent lectures, and I'll say some more words later. These include increased attention on adaptation, participatory processes, observed impacts, regional emphasis on oceans and urban areas in particular, and cross-border impacts. And there's also been a shift of emphasis towards bottom-up approaches, ensemble impact modelling, behavioural modelling, economic assessment, and cross-sectoral analysis. There have also been enormous advances in research related to vulnerability and adaptation, and these have been highlighted in the recent 6th assessment report that was released just this week. These relate to research into adaptation solutions for enhancing resilience and principles of justice in managing the transition to a sustainable future that's also fair and inclusive. And you'll hear about many of these and more in other webinars to come. So realizing that some future climate change is unavoidable, policymakers around the world are starting to pay serious attention to climate change adaptation, with adaptation support tools commonly deployed for this purpose. These are often designed around the adaptation learning cycle, for which several methodological guides are available. The European Climate Adapt support tool is shown here. It includes elements that may require CCIV methods and tools at different steps of the cycle. For example, risk and vulnerability assessment methods in step 2, or economic analysis to assess adaptation options in step 4. Consistent with this emphasis on decision support are moves towards treating adaptation policy in a risk management framework. And the IPCC has developed a risk methodology for undertaking its assessments, where risk is defined as the potential for adverse consequences for human or ecological systems. Risk is represented as a function of a climate hazard, exposure to that hazard, and vulnerability to the effects of the hazard. Note too that risks can arise not only from potential impacts of climate change, but also from human responses designed to address climate change. The concept of risk is understood in many ways from varying perspectives, and the IPCC has developed a very informative guide for authors of the 6th assessment report that I would commend to you. Finally, a focus on adverse impacts and related terms, risk, hazard, and vulnerability, is understandable given the objectives of the Framework Convention shown earlier. And this also underpins 5 reasons for concern used by the IPCC to define dangerous levels of change. However, it should be viewed as a framework for the assessment of research rather than an analytical framework for undertaking research. For instance, a focus on the risks of climate change should not imply that there are no opportunities as well. Positive, negative, and neutral outcomes should all be discoverable in any policy-neutral analytical framework. CCIV assessments nowadays are increasingly directed towards real-world problems facing decision makers and practitioners who need to design effective responses for adapting to a changing climate. Thus, for research to be relevant and credible, it's essential to work closely with key stakeholders. The benefits of such participatory processes include helping to ensure salience or relevance of the results, joint ownership of the research, opportunities for shared learning and for enhancing skills and expertise, improving equity in decision-making by promoting participation in project planning, implementation, and evaluation. And such processes can also be cost-effective in the long term through the opportunity to test and appraise ideas before their adoption. So now let's turn to some of the more common research methods of analysis by first considering climate change impacts and adaptation that have already been observed. How can we identify those? Observed impacts are observed changes in natural and human systems in response to observed recent climate change. There's been much research in the past 2 decades into detection and attribution. These terms can be applied both to the climate change itself and to impacts of climate change. And the figure illustrates some of these distinctions and is explained further in the notes in the book. Essentially, detection is concerned with demonstrating that change has occurred in a statistical sense, whether in climate or some system affected by climate, but without providing a reason for that change. Attribution is where the relative contributions of various causal factors to detected changes are evaluated along with an assignment of statistical confidence. Finally, observed adaptation is a response in natural or human systems that modifies an impact attributed to climate change. And there's already evidence of spontaneous observed adaptation in some human systems, and it's of increasing policy importance in relation to the monitoring and evaluation of adaptation measures. After discussing climate change impacts and adaptation that have already been observed, now let's consider how to analyse those that may occur in the future. One approach is to use analogues. Spatial analogues use information on present-day climate conditions, impacts, and adaptation strategies from another region that may serve as an analogue of future conditions in the study region. Here we show an earlier example of this. Arrows from a set of case study regions in black point to analogue regions that are hatched, having current climate similar to a future climate under doubled atmospheric CO2 simulated for the study regions by a global climate model. For example, Iceland's future climate resembled that in northern Scotland today. Temporal analogues use information from previous time periods that may serve as analogues of conditions expected in the future. These may be event-driven, such as extreme climate events like droughts or storms, large-scale events producing anomalous impacts, such as the El Niño Southern Oscillation phenomenon, or benchmarking events, such as a 100-year flood. And the example here shows two past mild winters as analogues for future skiing conditions in a warming northeast US, showing snow conditions, shortened ski season, and reduced visitor numbers. Some of the advantages and disadvantages of these analogue approaches are discussed in the book, and you may also have noticed that the variable spelling of analogue in the book has been one casualty of a transatlantic editing process. Another way to simulate impacts under a future climate is to conduct physical experiments. Artificial environments can be created that replicate anticipated future conditions, for example, of climate, fresh water, or atmospheric composition. This offers a possibility to conduct physical experiments of system responses. Various examples of such experiments have been reported, including for agricultural crop yield, the photo at the top right, tree growth and productivity, there's a photo on the left there, lake ecology at the bottom right, as well as pest response, durability of building materials, and there are other examples as well. And such experiments, whether they're in the laboratory, greenhouses, chambers, or the open air, can provide valuable information on how systems respond to changed conditions, which in turn may then contribute to the development, refinement, and calibration of impact models. And it's impact models that we consider next. The most common approach for investigating future impacts and adaptation is through the use of models. Impact models are used extensively in research for representing responses of a modeled system to climate change based on a knowledge of the main causal mechanisms determining the sensitivity of a system to climate and to other key drivers. Adaptation processes may also be simulated. And there's an enormous diversity of impact models, which are classified here into just 4 types, which are not mutually exclusive. Statistical correlative models, process-based biophysical models, behavioral models, and economic models. And I'll talk a bit more about those in a moment. Most focus on single sectors or themes, and they have different methods of representing system behaviors. Impact models have been developed that operate at widely different spatial and temporal resolutions, depending on their purpose. Recent developments in impact model include the use of multi-model ensemble simulations for representing uncertainties within and between impact models in combination with scenario uncertainties. This can be very instructive for assisting model development to address those uncertainties. I'll just illustrate each of the model types briefly, but there'll be numerous examples of model-based analyses presented in the later lectures. In this figure, we show a typical statistical correlative model for the transmission of a vector-borne disease in China. This is currently limited by January temperatures to the green area, but poses a risk of expansion as January temperatures increase, shown as the blue area, which represents a scenario for 2050. The next figure illustrates a typical process-based biophysical model, which seeks to simulate key processes relating environmental conditions to grain yield response. This example distinguishes between potential, attainable, and actual production. Progressively greater model complexity is required to address processes and constraints at each of these levels. The right-hand figure illustrates typical outputs of such process-based crop models. Aspects of impact model uncertainty are represented, with different models producing different simulated outcomes that can also be compared here to observations. Knowledge of these uncertainties may help to judge confidence in model-based projections. Behavioral models are developed to study individual and social behavior in decision-making, such as for adaptation and mitigation. And these include a range of agent-based, multi-agent, and microsimulation approaches to describe the behavior of different actors. And the figure here shows some types of behavior represented in a survey of models for land-based sectors. The height of the bars represents the number of models depicting the type of behavior shown, with the colours referring to different land uses. This study found that economic-based decision-making remains the dominant behaviour modelled. Behaviours such as diffusion, interaction, anticipation or learning are relatively neglected, and dynamic behaviours, objectives or decision-making processes are almost absent, despite their clear relevance to climate change responses. Economic models are of many types, operating at different scales. The main groups of methods in adaptation economics have been summarised in the diagram on the right. The authors of that review distinguish between, first, more conventional economic decision support methods, such as cost-benefit analysis, cost-effectiveness analysis, or multi-criteria analysis, and second, techniques that more explicitly address uncertainties. They emphasise that economic analysis of impacts and adaptation is not just a question of costs or financial return of projects, but commonly need to address such issues as trade-offs, generational issues, or robustness across multiple futures. They might deploy methods such as iterative risk management, real options analysis, robust decision-making, or portfolio analysis, and some of the later lectures will tell more about those methods. Integrated assessment approaches explore linkages and feedbacks between key drivers and responses in natural and human systems. These include socioeconomic and technological drivers, greenhouse gas emissions, climate, biophysical impacts, and economic impacts across multiple sectors and scales. These are usually set up as standalone numerical models, though soft linking of independent impact models is sometimes applied, and expert judgment is used in some assessments where processes cannot be formally modelled. An example of a regional integrated assessment model for Europe is shown here, which links a set of reduced form sector-based models to simulate the cross-sectoral effects of different climate and socioeconomic scenarios across Europe. Users can also adjust input variables to simulate adaptation processes. This model and the approach are explained in greater detail in lecture 17. Integrated approaches can be instructive for representing synergies and trade-offs between sectors, for showing how certain types of outcomes may differ greatly from those simulated using single sector models alone, and for informing integrated cross-sectoral policy responses. However, such models can be complex to develop and test. They commonly have demanding data requirements, and they often require simplification of process descriptions. Sensitivity analysis is a standard method for testing the effect of adjusting key parameter values in a model. It can also be usefully extended to test other model behaviours, for example, by constructing impact response surfaces for showing impacts under climate that's been altered systematically across a plausible range of future changes. The analysis is scenario neutral, as it does not rely on detailed climate model-based projections, yet it can still help to test a model's behaviour and fitness for application under changed climate. It can also be extended to investigate thresholds of change at which critical impacts occur, as well as likelihoods of crossing such thresholds in the future. For example, this set of plots shows how 30-year average wheat yield responses to systematic temperature and precipitation changes relative to the current climate, as simulated by 26 different process-based crop models for a site in Germany. The response surfaces can be used to compare behaviour across different models to gain a better impression of uncertainty in yield outcomes. Vulnerability assessment refers to a common approach often used when there aren't other impact models available for representing indicators that may contribute to potential impacts of climate change. And it's worth pointing out that the term vulnerability is used in at least two senses by researchers. The first is as a potential impact, where vulnerability is related to exposure, sensitivity, and capacity to adapt to a changing climate. And this is often referred to as outcome vulnerability. The second sense is as a social or ecological setting for examining climate-related risks, as shown earlier in slide 8. It's referred to as contextual or starting point vulnerability by the IPCC. Vulnerability assessment often involves mapping of indicators and has been used in different contexts, for example, to investigate risks of climate change, to focus on social aspects of vulnerability to climate change, or to examine resilience and capacities for coping and adaptation. The example here shows an interactive and exploratory online tool for mapping a composite index of outcome vulnerability. The map on the right depicts the vulnerability of the elderly population to climate change in Finland, which combines user-defined indicators of exposure and sensitivity to climate change, the map on the left, and adaptive capacity, the map in the middle. Cross-border or transboundary impacts of climate change refer to impacts that occur outside the borders of a region of interest, but may nevertheless affect that region. This is a relatively new area of research, though it's been recognised in some countries for well over a decade. Preliminary analysis for Europe suggests that some European countries may be more vulnerable to cross-border impacts of climate change, for example, due to strong trading or financial dependencies, than to direct impacts of climate change occurring in the countries themselves. Cross-border impacts pose interesting jurisdictional as well as geographical challenges for adaptation. A number of different pathways of cross-border impacts have been identified in the literature, but differences between classifications are minor, and the example for Finland shown in this figure is typical. They include trade, biophysical, infrastructure, human mobility, financial, and geopolitical pathways. An additional aspect not shown in the figure relates to the role of human perception in amplifying or reducing the propagation of such impacts. Lecture 18 touches on this topic, and I've also provided links to 2 international projects on the theme that are currently being funded by the European Commission. We've explored methods of analysing future climate change impacts, but what assumptions can analysts make about the future? Futures analysis is concerned with describing plausible future conditions, commonly referred to as scenarios, that can be used both in research and by decision makers in exploring available options in the context of high uncertainty. 2 broad classes of scenarios are commonly applied in climate change research, though some scenarios combine aspects of both. Exploratory scenarios combine narratives with quantitative model projections of plausible future developments and key drivers of change. Normative scenarios describe visions of desired or targeted futures. The table on the right from the IPCC Special Report on Land classifies types of exploratory and normative scenarios commonly approached in climate futures analysis for the land sector, though these are readily transferable to other sectors as well. Scenarios are often key elements of the analysis of future impacts and adaptation, and we've described in earlier slides. And global scenarios used in climate change research are frequently constructed by the international research community. On the other hand, regional and local scenarios usually require strong stakeholder participation to ensure their relevance and acceptability, especially if they're to be applied in decision making. And we can examine these a little bit further now. So at global scale, the so-called RCP-SSP Global Scenario Framework was developed over a decade ago by the international research community to serve the needs of researchers and policymakers working in the field of climate change. Representative concentration pathways, or RCPs, are trajectories of greenhouse gas and aerosol concentrations in the atmosphere that affect the radiation balance and hence the climate. These trajectories were simulated by integrated assessment models. The 4 original RCPs were selected to span a representative range of radiative forcing values found in the literature, in watts per meter squared by 2100, ranging from 2.6 to 8.5. That's the left-hand graph at the top there. They were intended as inputs to climate models as part of the CMIP-5 model into comparison exercise that was assessed in the IPCC 5th assessment in 2013. RCP-based climate projections are illustrated in the left-hand graph at the bottom and sample global maps on the right. Other information is also available from these exercises, such as projected sea level and atmospheric composition. CMIP-5 model outputs have subsequently been used in impact assessments, often downscaled to regions of interest. And you can hear more about these downscaling methods in lecture 4. The SSP part of the global scenario framework refers to shared socioeconomic pathways. SSPs are 5 alternative global development pathways that contain qualitative descriptions of trends in societal development at the level of large groups of countries, as well as some quantitative projections at the national level. They include key socioeconomic drivers of greenhouse gas emissions. They also describe socioeconomic developments that may be useful as input to impact models used for scenario-based research. For example, population, income, urbanization, technology, and educational attainment. Such drivers can help to characterize vulnerability and exposure to impacts of climate change. The 5 SSPs are organized with respect to challenges posed to adaptation and mitigation, as we see in the figure there. The global SSPs have been extended to finer scales and sectors and can be combined with RCP-based climate projections to form integrated scenarios for application in regional and local impact assessments. This enables analysts to explore uncertainties not only in climate futures, but also in aspects of vulnerability and exposure. Many of these studies show high sensitivity to assumptions about societal development. The table on the right illustrates which integrated scenario combinations were most popular in the reviewed literature up to 2019. The rows indicate levels of radiative forcing consistent with different RCPs. The columns show the 5 different SSPs. Darker colours show the more popular combinations. The table also hints at developments not discussed in the book, but important to understand now that the IPCC 6th assessment reports are being released. The newest climate model projections assessed by the IPCC are now all based on variants of the global socioeconomic pathways described by SSPs. They are also now labelled as SSPs. So on the left here is a figure from the IPCC that David also showed, released just last year, where new global mean temperature projections are shown for five pathways of radiative forcing out to 2100, labelled as SSPs. The numbers at the end of the names reveal that 3 are equivalent to the earlier SSPs, 8.5, 4.5, and 2.6, and 2 are new, 7.0 and 1.9. For this reason, too, it's probably more accurate to describe the framework now as an SSP-based rather than RCP-SSP global scenario framework. While a large focus of recent work on impacts and risks has been directed towards adaptation, there are cases in which conventional adaptation measures may fall short of what's required. This is where innovative and transformative solutions may be required. These are adaptation responses that change the fundamental attributes of a social ecological system in anticipation of climate change and its impacts. An example of how the concept of transformation has been tackled in earlier work is shown on the left here from the Impressions project for Europe, which will be spoken about more in lecture 17. It illustrates how normative and exploratory scenarios that I just introduced can be combined in analysis with strong stakeholder participation. And here, success in reaching stakeholder visions for a future sustainable Europe is represented using some key indicators. The red line illustrates how the future evolution of these indicators can be modelled for a range of RCP-SSP scenarios. Then the shortfall compared to the vision defines the challenges for adaptation and mitigation. Some of these actions can be modelled too, and their effectiveness evaluated. If they still fall short compared to the vision, then there may be a need for some more radical, stakeholder-led, transformative solutions. To this end, as shown on the right, different options for attaining the vision can be explored, here illustrated as alternative strategies and pathways. These are sustainable solutions that recognise possible synergies and trade-offs between adaptation, mitigation, and other sustainable development objectives. So to conclude this brief introduction to the assessment of climate change impacts and adaptation, I've tried to pull out a few messages that I think are worth highlighting. First, the societal and policy relevance of climate change impacts, adaptation, and vulnerability research has never been greater. In this light, secondly, adaptation-led and vulnerability-led approaches to analysis are increasingly emphasised. Third, while risk framing of adaptation to potential adverse impacts is entirely appropriate for serving policy, researchers should continue to apply policy-neutral methods of analysis in which adverse, neutral, and positive impacts of climate change are all discoverable. Fourth, several new research topics are receiving increased attention, including observed impacts, cross-border impacts, ensemble impact modelling, behavioural modelling, economic assessment, impacts on oceans and urban areas, and cross-sectoral analysis. Research on feasibility, effectiveness, and justice in the implementation of adaptation were not listed here, but I'm sure that these topics and many others will be raised in later lectures. Fifth, integrated global SSP-based scenarios are increasingly being adopted in impact and adaptation studies to acknowledge the important role of future socioeconomic development in conditioning future impacts and risks. And six, adaptation strategies and pathways can be usefully informed by participatory methods that combine both normative visioning and exploratory scenarios. And I'd finally just like to close on a more personal note. I'd like to acknowledge that if it wasn't for Martin Parry, for whom this lecture course is dedicated, I might never have entered this fascinating field of research at all. It was Martin, following an interview at the University of Birmingham that he already mentioned in 1980, who offered me the chance to work for a PhD on this topic, and then to accompany him to EASA in 1983 to begin a research career on climate change impacts and adaptation. So Martin, I feel immensely fortunate and privileged to have worked with you over all these years. Thank you so much. And thank everybody so much as well.
Thank you so much, Tim. That was great. We already have a couple of questions, and if people have questions, please type them up. And let's go into the Q&A. So we have one question from Leonard. Thank you, Leonard. In modeling climate change, impacts on crop production, there are several sources of uncertainties, from calibrating the crop growth models, predicting future climate, the future management of crops, and the interactions. How confident are we about modeling predictions, and how about the actual climatic conditions along with the management at the time?
Okay, very good question, and a very, very important question, of course, for food production and food availability worldwide in the future as well. And yes, of course, there are many uncertainties. I was just giving a more sort of generalized overview of different types of modeling methods, but crop modeling is something that I've done a bit of work on myself, and Martin Parry too, for that matter, and Cynthia. So they're probably better able to answer this question than me. But I think as we now have done a lot more, we put a lot more effort in the last 10 years or so into testing our models for representing crop production, including not only the physical sort of responses, but also management and other issues. And we have these model intercomparison projects, including one that Cynthia herself is leading, the agricultural model intercomparison and improvement project. I think we are much more confident now, probably, with our projections than we maybe were 10, 15 years ago, when there was a bit of a lull in interest and a lull in funding as well, for that matter. So, of course, many uncertainties remain about many of the assumptions that go behind these models. And of course, the economics of food production, probably just as important as the physical side as well. But if anybody else wants to comment on that, they're welcome to.
Manishka, so I can make a brief comment as far as the climate side of the issue. I think rising temperatures and more extremes are pretty well guaranteed for many agricultural regions. I think the impact on water availability is very uncertain. And so what I would think is, and also cloud cover. So what I would think is that agricultural models need to consider a wide range of possible, especially hydrologic states that their future agricultural regions will possibly experience, along with rising temperatures.
And just to hop in to say, that's what we do in AgMIP. Multi-model approach, rigorous protocols, scenarios around each one of the components that and factors that Leonard raised in his question. So you know, it doesn't get. I would say that the challenges of impact modeling doesn't get any easier, but more and more we're handling explicitly more of those uncertainties, but still then looking for the general findings that we can then can work with the regions, and in this case agricultural regions, both the regions within countries and the national planners, to develop resilience strategies. It's the evidence base for that. Great. Okay, Manishka, I think we need to go to Rosalva, right?
Exactly, yes.
Thank you, Tim. It's great.
Hello, everyone. My name is Rosalva, and I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies. And I am grateful for the opportunity to share about some NASA supplemental resources that may be helpful for students and teachers who may be joining this session. Can you see my screen now?
Yes, thank you, Rosalba. That looks great. Thank you.
So I want to share about NASA's Global Climate Change site. The link is climate.nasa.gov. It's a very comprehensive site. So it could be helpful, again, for students and teachers or anyone that is interested in climate. You can access facts and data about carbon dioxide, global temperature, Arctic sea ice extent, ice sheets, sea level, ocean heat content. There is also a section explaining the causes and solutions to climate change, including adaptation and mitigation strategies. There is also a very good section, especially for educators and for students, with quizzes and interactive tools and videos, articles, and news. So definitely something that I encourage you to explore. As part of that climate site, you will also find a tool that is called Earth Now, or Eyes on the Earth. The QR code to access it is on my screen now, but I also posted a link in the chat. And so with this tool, you can access a 3D visualization of our planet's vital signs. So you can monitor sea level height, atmospheric carbon dioxide concentration, Antarctic ozone, and many other parameters. You can also access information about the satellite missions that are getting these measurements, information about each instrument on the satellite. It is a pretty, it's also pretty fun to use, but again, a very good tool for students and for teachers. Next, I want to highlight ARSET, that stands for Applied Remote Sensing Training. So this team at NASA provides accessible and free training on remote sensing satellites, sensors, methods, and tools. The trainings are open to everyone. They are sometimes online, sometimes in person. Right now, because of the pandemic, they're still just online. Sometimes they are live with an instructor, and sometimes there are others that you can just take when you have time on your computer. There are different levels, and the topics range from disasters and health and air quality and land management to water resources and climate. And I want to especially highlight this training, so you can find the recording. Again, I posted the link on the chat. For this training, titled Introduction to NASA Resources for Climate Change Applications, that was co-produced by ARSET and the NASA Goddard Institute for Space Studies, and it provides you with an overview of NASA resources for monitoring climate change and its impacts, an overview of the climate models that are used to assess impacts, and also an overview of resilience applications. Next, I want to also share with you about 2 unit plans that were developed for high school students by high school teachers that worked with us at the NASA Goddard Institute for Space Studies as part of a program called the Climate Change Research Initiative. And so on my screen, I have a summary of one of these units. The title is Future Temperature Projections. And so with this unit, the students can learn to analyze and evaluate future temperature projections up to the year 2100 using the GISS, the Goddard Institute for Space Studies model, E2, and also through representative concentration pathways scenarios, such as what Tim was mentioning before. This unit assumes that the students already have some background knowledge about Earth's energy budget and greenhouse gases emissions, but if they don't, this teacher also developed a unit that is called Earth's energy budget. I also posted a link in the chat so that they can learn about that. This was developed by Ms. Nikki Delaney. So again, one of the high school teachers that have worked with us at the Goddard Institute for Space Studies, and she was mentored by Dr. Legrand, one of our NASA scientists. And also I want to highlight this other unit plan. The name is Urban Surface Temperatures and the Urban Heat Island Effects, that was developed by another high school teacher that has worked with us, Alejandro Mundo, who was mentored by Dr. Christian Brania, one of our NASA scientists at the Goddard Institute for Space Studies. And with this unit, students can learn how the climate is changing in urban settings, but also how to produce mitigation solutions. And so in fact, the unit concludes by having the students create a physical model that promotes the concept of the urban heat island effect and also some mitigation factors to deal with these extreme heat events. And that's it for me. I hope that this is helpful. Thank you.
Rosalba, thank you so much. And Rosalba, want to share, of course, with everyone that Rosalba is a leader at Goddard Institute for Space Studies in the STEM engagement, working with teachers and students around all of the science of climate change and impacts and adaptation. So Rosalba, thank you so much. We're now at our wrap-up period time. We're going to go a few minutes over, but please stay on if you can, because we want to hear once more from Martin, final word, then Manishka, and then I'll do a very quick wrap-up at the end, and we'll show the schedule. That we're going to show the schedule for the rest of the webinars. Martin, over to you for a final word.
Okay, Cynthia. Thank you very much. I hope everyone can hear me okay. Thank you very much, David and Tim, for such excellent presentations. I think they're a great example of what we can expect over the next 12 weeks. If I can, 2 times 12 is 24. Yeah, 2 lectures per session makes just about the 25 lectures in this book. And it's driven home to me again, actually, what a great idea that Cynthia and David Rind had as editors of this series. We're in volume 2 now, of putting together a published book that is slide based, and to be able to see these slides and think to myself, well, I need to know more about that. I can go to the notes on each of these slides to learn more about them. They are really it's really a great learning tool. I'm not patting my back here. This is not my idea, but it's also, of course, a great teaching tool. And I really wish, when I was a lecturer at university, which seems ages ago now, I had something like this available to get started with, because it's essentially 25 top-class lectures by the best people in the world to do it, backed up by the notes. So thank you for that. One other thing I want to mention is just as an indication how far things have come in the last 15 years, some of those with us may not realize that it's only, 2007, Cynthia, that you led a chapter on detection and attribution, which was the very first by the IPCC, which we pushed into that volume of the 4th assessment. We fought it through 2 nights of plenary against several countries' representations, delegates that won't be mentioned here, as it was seen by them to be pushing too far. And now, of course, it's an entire field in itself. The observing of climate impacts, the detection, attribution of them to climate change, and a lot of the current IPCC assessment published just on Monday this week, Tim mentioned, is concerned with this, the pace at which we can measure the impacts of climate change now. So there, Cynthia, I haven't really said thank you to you and David so far, and I should do, for this volume, but also for including me in it. Thank you very much.
Hey, thank you, Martin, and you're very welcome. Manishka, over to you for your final thought for today.
Thanks everyone for your participation, and thank you to David and Tim as well. There are 2 other people I would like to thank. That's Jen Evans and Maria Dombrov, who've been working very hard to support the webinar series and also getting the word out about it. Just as Martin said, I think this is a fantastic resource, especially in regions where there is less access to such material. We will share the link to the recordings as soon as they're available, and we'll try to put them up within the next week or 2, and we'll notify all of you. Thanks so much, and on to Cynthia to wrap up.
Great. Thank you, David and Tim. Wow, what a great send-off, great launch for the webinar series. Thank you to the participants, everyone who came and who participated. Thanks for the great questions and challenging questions, and the opportunity for us to think together about these very real challenges as the climate changes are occurring, and the impacts and the adaptation now are in response to, for example, Ivan Biot's comments, so much taking hold now, so much front and center. It's about impacts and adaptation. Thanks to the participants. Thanks also to NOAA, CC Run, that's the Consortium for Climate Risk in the Urban Northeast. They are hosting the webinars on their YouTube channel. So thanks to Radley Horton and Bill Selecki and Franco Montalto. They're the PIs of that, the leaders of that, and Dan Bader, the coordinator who we are working with on the webinar series. And so with that, I think we're showing again in 2 weeks, March 16th. We're going to be hosting Linda Mearns, as was mentioned. She's a world class expert in regional and local downscaling for impact assessment, and Roger Pulwarty of NOAA, who is working also worldwide with WMO and American Meteorological Society, just pushing forward all of the aspects that Tim was bringing forward in his methods. He's going to be focusing on effects of and adaptation to extremes. So we hope to see you in 2 weeks, and thank you so much. Bye. All the best.